Hey, good afternoon, everyone. Y'all doing all right? Ready for the weekend? All right, so let me start class today with any questions that you might have. Is there anything that you'd like for me to go over homework-wise? Everybody did fine with the homework? Last call. Okay, so write this down. This is a quiz for today. You're not going to do this quiz in class. You're going to do it and submit it to me. And I'm going to put the link where you submit it in the chat, which I just sent. And I will also email everybody that link after class. All right. So I give you a function, f of x is 1 over x cubed, and I just ask you to find f prime of 1. I was going to have you do that in class, but I just don't want to eat up too much time. So take home quiz. All right, let's get down to business. So when we were doing last class, we were covering derivatives and rates of change. There's a topic at the end of that section that I didn't get to, but I actually am going to talk about it again at the end of the section we're going to cover today. So I'm just going to kind of kill two birds with one stone and skip it, but then we will cover it at the end of class today. All right, so it'll be incorporated, it'll just be a little bit out of order. All right, so we are going to now talk about the derivative as a function. And then next class we'll talk about, we finally get to throw away the limit next class, and I give you shortcut formulas to find derivatives, and you're going to be very happy. And that's it, that's our plan. All right. So the two main ideas from last class were that if you take a curve, function f, you go to some arbitrary point A, go up to the curve, we can find the slope of that tangent line by computing one of two limits, and it was our choice which one to use. We could do limit, the first one I showed you was limit x approaches a, f of x minus f of a over x minus a, or you could do the limit as h goes to 0 of f of a plus h minus f of a all over h. Either way, to find the slope of a tangent line on a function, you have to be able to compute a limit where you're going to get 0 over 0, and you're going to have to do some sort of algebra in order to get to a numerical answer. All right. I told you from these two different limits that we talked about, that this is the one that we would be using moving ahead. Moving forward, that's the one we would use more frequently. And so this section that we're going to start today, we're going to build off of this idea. Okay. So I'm now going to draw you again the picture from last class of how we came up with this idea. We said, okay, we're going to start, we're going to take some function, we're going to pick some point A, pick some other point A plus H, draw the secant line between them, and then try and move this A plus H towards the A. And to do that, we had to let H go to 0. And then that's how we came up with the formula, right? Does that look familiar? Well, in this section, what we're going to do, this new section, is we're going to use this same picture. Okay, I'm going to take this same exact picture, but instead of using the letter A here, right? Instead of using A, I'm going to use X, right? So if we replace this with X, we replace that with X, then it's the same limit here, right? It's the same limit, this same thing. Let me copy it. Except now what we've done is we've replaced the a's with x's. So it becomes this limit h approaches 0, f of x plus h minus f of x all over h. So the exact same formula with x's in place of the a's. And you're probably sitting there, but what the, like, why do you keep on changing all these letters on me, right? Well, look, back up here, when I was introducing this concept, the a was a fixed number, right? We came here and we fixed this point a, right? We fixed it. We said, okay, let a be 2 or let a be -1 or whatever it was. And it was easy for us to understand that that's just some value on the x-axis. What we want to do now is think about that value as being arbitrary, that it's a variable. It's allowed to be anything we want it to be. And if we do that, then it seems natural to want to call it x instead. That gives it some implication that it's not stationary, not fixed. And so just replacing that with x and x, we get this new formula. Well, remember also, and I should have stated this earlier, that at the end of class last time, I said this, instead of me telling you to do this over and over, I'm going to give you a new notation. We called it f prime of a. Remember that? F prime of a. That's what both of these meant. Well, if I'm now going to replace the a with x, right, then this down here is now what we call f prime of x, right? It's just same thing, just replace the a with x. This right here is the new formula that we're going to be using pretty much for the rest of the class, all right? This formula. Now, any questions on that? We're just replacing a with x and we've got this new formula. That's it. Now, before I get into this, I want to make sure that you understand something that's going to seem simple at first. All right. I'm not trying to insult your intelligence here, but as long as I've been teaching this, students have trouble with this for some reason. If I give you a function, right? Let's say I call it, let's call it g, okay? And I tell you this, that g of 2 equals 4. Then that means that when you go out to the right 2, you have to go up 4, and that's where you have a dot, right? You plug 2 in, 4 comes out. If I tell you g of 5 is 3, that means if you go out to 5, you plug in, and that value over here is 3. Make sense, right? I mean, we should know this. This is the input, this is the output, right? In and out. All right. All right, here we go. Let's see how you do with this. This is going to be very visual. Okay, this is everything I show you is going to be a very visual thing. So let's see if you can grasp this. Let me bring up my notes. Okay, the first part of my notes is just explaining that I'm going to now rewrite this f prime of a, and I'm going to replace all the x's with a's, and we get this new thing. All right, and that this new thing represents the slope of the tangent line at x. Say that again. This new limit represents the slope of the tangent line at some value x, right? Used to be a, but now it's x. All right. So I'd like for us to look at a function, all right? You'll see this. This is some function. Let's just say that, this is the function. It says here, oh, hold on. I got to open another program. Give me a second. I forgot that I restarted my computer this morning. Where is it? There it is. Okay. So this is some function here, f, right? This is the f function that we're looking at. And what I'd like for us to do is start talking about the slope of the tangent line at different points. So I'm going to go here to -1, right down here. We take that point, and I want you to think about what the slope of that tangent line looks like, right? What does the slope look like? You all agree it would be something like this, right? Now, is that a positive slope or a negative slope? Don't remember with lines, right? If the line is flat, it has a slope of 0. If it's pitched up like this from left to right, right? If it's pitched up like this from left to right, the slope is what? Positive or negative?
Positive.
Positive.
Right? And if it slopes the other way, then it's negative, right? We're all clear with that? So would you all agree with me if I said that the slope of the tangent line, the slope of this tangent line here, let me do a different color. The slope of the tangent line there, I'm just going to call it M, that it is some positive number. Agreed? Okay. Let me bring in my little guy here. Come on, man. I'm going to go to that point. Now I'm going to have the computer put the tangent line there for me. There it is. Let me clear all this out. So that has a positive slope. Yes. Now I want to draw on top of that. There's that one, right? There's that line. Now let me move that point somewhere else now. I'm going to move that point over. Let's put it right there. Okay. So Landon, are you here?
Yes, sir, I'm here.
Okay, what about the slope of the tangent line there? Positive or negative?
It is positive, sir.
It's also positive, right, everyone? We agree the slope is positive there? It's positive, right? So it would look something like that. So that has a positive slope, that has a positive slope. Now, Landon, let me ask you, which of these two are steeper? The one on the left or the one on the right?
The one on the left.
Okay, and if it's steeper, that means the positive number here is bigger or smaller than the positive number here?
Bigger.
Bigger. Bigger number, okay, when we're talking about slope, bigger number means steeper line. Smaller number means less steep. 0 means no slope, right? Flat. Negative is the other way. Got it? Okay, let me keep moving. How about if I move to right here at the top of this thing? Hello, are you there?
Yeah.
What do you think the slope of the tangent line is there at the top?
Mm,
Is the line pitched up or down, or is it flat?
flat.
It's flat, okay? And flat lines have a slope of
0.
0. It has a 0 slope there, all right? Now, Hele, what happens if I move a little bit to the right? Let me just move over a little bit over here. That slope would be positive, negative, or 0?
Negative.
Negative, right? Everyone see that has a little negative slope there? Okay, so if I draw that slope, let me do a different color. That has now a little bit of a negative pitch to it. And then, Hele, let's just keep going. What if I move a little bit more to the right? Hele, is it positive or negative?
It's still negative.
Still negative, but compared to this negative one, this should be more negative, right? Which means a bigger negative number. So like maybe the slope here is -1, this would have to be like -2 or something like that. That makes sense, everyone? Y'all sure? Okay, I'm gonna clear all this out of here.
Can you repeat that last thing? Like this.
Okay, if we had a point here and we had a negative slope on it, but we had another point here and another negative slope, but the pitch of the line, this blue line on the right, the pitch is steeper down, which means the negative number here would have to be bigger than this negative number here. So let's just say this was -1. Let's just say that was the slope there. This would have to be something like -2 or maybe -2.5 or -3, whatever, but it's definitely a bigger negative number than -1. Make sense? Okay. So let me see if let's see if we can wrap our heads around this. At every value of x we ever pick, right? At any value of x you ever pick, right? Any point, you can come down to the function and you can find a slope of a tangent line, right? At every single point, there's some slope of a tangent line. And it's either going to be positive or negative or possibly 0, right? And the size of those numbers depends on the pitch. Yes? So I'm going to create a new function, a new one, not this function, a new one. And what it is a new function that the input, the in is going to be the x, okay? And the output is going to be the slope of f, of this function, okay? But it's a new function. Remember, functions take things in and spit things out, right? Take something in, spit something out. So I'm going to create a new function that's going to take the x value, whatever x value I'm at here, and then it will spit out the slope of the tangent line on this red curve. So I can illustrate this with the computer. I'm going to clear this out. Let me show you the tangent line. So do you all see that at this particular x value that I'm out right now, it was a positive slope, right? And I have the computer telling me what the value of it is. Okay, now don't ask me how I got that number, but the computer is telling me that the slope of that line is 2.83, right? So I've got this new function that takes in this input. Let me move the point to the right just a little bit. Let me move it to about 1, right about there. Let me clear this out. So if I go to -1, right? This is -1 on the x-axis. This new function takes -1 in, right, as an input, and the output is the slope, and the computer is telling me it's 3.23, right? So this new function has an input and output, and I can plot that input and output as a point on this grid. Here's the point. You see it right here? It has the input of -1, and the output is 3.23. Yes? This green dot is raised up 3.23 units. That's how high that point is. That corresponds to the pitch of this green line, right? The pitch of this green line is dictating how high that point is. If I move to the right, what should happen to this point? If I move this to the right, what's going to happen to the pitch of the line?
It'll get steeper.
It looks like it's going to get a little bit steeper, right? And then we get about here, and now what's going to have to happen? What's going to happen? Look at the pitch of the line. The pitch of the line is coming
Going
down,
down.
getting smaller. Still positive, right? Still positive. So we have a positive number here, but do you notice it's getting smaller than it was before? And as I keep moving, when I get to there, look at what is happening to that green dot. It hits 0, right? It hits 0 there because that's what the pitch of the line is. And then what's going to happen when I move to the right? Let me ask somebody. Nicholas, are you there?
Yes.
So what's going to happen, Nicholas, if I keep moving this black dot to the right, what's going to happen to my green dot? Where's it going to go?
They're gonna go down.
It's going to go down below the x-axis, right? Because the green dot is the slope. And if the slope is negative, then the green dot has to go below the x-axis. So it's going to go down, right? And then what's happening? Steeper negative, right? Steeper negative, bigger negative number. Watch that green dot get bigger and negative, right? And we get to about right here. And now what's going to happen to that green dot? Anybody? Still negative, but what? Where's it going to go?
Less negative.
I'm sorry?
It's gonna be a bigger negative number.
Okay, so if I keep moving this point to the right, think about the pitch of the line here, right? What's going to happen to the pitch of this line? Isn't that pitch of the line going to get less steep as I reach the bottom, right? It'll still be negative, but less steep, which means this green dot should start to go back towards 0, shouldn't it? It should still stay negative, but it should go back towards 0. And that's what it's doing. And now we get to the bottom, and you see at the bottom, the slope is 0. So we have a green dot that's 0. See, look, as long as I've been teaching this, this idea is something that either like, yes, you got it, or if the light bulb doesn't go off, you're like, what the hell's going on? Okay. Let me back everything up. And what I'm gonna do now, which is gonna be really cool, is I'm gonna do dots. I'm gonna do green dots for, as I move from left to right, I'm gonna do green dots, but I'm gonna leave them there, okay? Meaning I'm going to basically create a curve off of all of those dots. That green function represents what is happening to the slope of the red function at every point in time, or every point on the x-axis. That makes sense or not? This green function is called the derivative of f. It is a new function though, okay? We start with the original function f. From that original function, we can create a new function, which is its derivative. And that derivative tells us about the pitch of the line on the red, the pitch of the tangent line on the red function at every point in time. Okay? We're going to do more. Okay, we're going to do more of these. I hope that you understand that. Let's bring another example in here and let's see if you can kind of figure out what the whole goal here is. This: I give you a function, I draw it for you, and you draw me its derivative. That's what I need you to be able to do. I hand you a function, show you the picture, and then you go draw me the derivative. Let's try one. Let's take this one right here, just a horizontal line. So I think I'm going to do this on a separate page here. Let's say we have this function here. We'll start with a very basic function here. 1, 2, 3. So 1, 2, 3, 2, 3. See if I can connect those with a straight line. Where the hell's my shape? Where are my shapes? They're there. All right, let's take a look at this function. This is the function f. I want us to sketch f prime of x, which means the derivative, right? That means the derivative of f. I want us to sketch it. So let's see here. Sophia, are you here?
Yes.
Okay. Got it? Okay. I think it's because you have two devices on. So Sophia, let's just pick an arbitrary point. All right. Let's just pick any point. So how about if I pick 3? I tell you to go up here. And can you tell me the slope of the tangent line?
For spot 3?
Yeah, at 3, you go up here to this point. Can you tell me the slope of the tangent line for this graph? Maybe I should point out, Sophia, isn't the red graph a line already?
Yes.
Right? So if I wanted the slope of the tangent line, the slope of the tangent line should be parallel to that line. Do you agree with that?
Yes.
Can you tell just from my picture, Sophia, what the slope of this red line is?
Yeah. It's is it at y 8, the spot x3? Oh, is it?
Wait, say again?
Is the slope 3?
Yeah, the slope of that red line is 3. Do you all agree with that? The slope of the red line is 3, which means that if I go to like the point 3 and go up there, the slope of that, Sophia, should also be 3, right? The tangent line?
Yes.
Okay, so let's graph that function. You said when I plug in 3, it spits out 3, right? That's what the derivative is doing. You plug 3 in, it spits 3 out. Let's keep going, Sophia. How about if I plug in 2, Sophia, and go up here? What's the slope of the tangent line?
3?
3, right? So if I plug in 2, I'm going to get 3. What if I plug in 1, Sophia?
You're gonna get 3.
3. And doesn't it not matter what I plug in? I'm always going to get 3, right?
Yes.
So the derivative, if I were to look at this as a function, you plug in 1. I'm about to graph the derivative. I'm going to do it in green. When I go to 1, I go to 3. When I go to 2, I go to 3. When I go to 3, I go to 3. When I go to 4, I go to 3. When I go to 5, I go to 3, 6, 3. Any input, right? Any x value, you're always going to have the same output for the derivative. So it's just, isn't the derivative just going to be this function here?
Yes. So the derivative is just the number of the slope of the original line?
Yes. Now, Sophia, it's an easy problem when the original function is a line, because if the red function is a line, then it always has the same slope, doesn't it? And so your answer would be 3, which is just the slope of the original line. What I'm trying to get y'all to see, though, is that the green thing out here, the green graph, is actually a picture of the derivative. Okay? It's a picture of the derivative. Things get hard when f is not constant, when f is, I'm sorry, when f is not a line, which is the next example. All right, so let's take a look at the next example, this one. Now, this example, I have intentionally colored the function green and red, and that's to help you see that when you're on the green sections, well, can someone tell me when you're on the green parts of this function, what the derivative should be, like in terms of positive or negative? What do you all think?
Positive.
It's got to be positive, right? On the green parts of that function, your derivative needs to be positive. On the red parts of the function, that derivative should be negative, right? Because you're going down. And then what about at these 2 black points? What should the derivative be there? What's that? 0, right? Think about if you were to take the tangent line right here, it'd be 0. The tangent line here, 0, right? The slope would be 0 here, slope would be 0 here. And then anywhere between, it looks like between 0 and 2, my derivative will be negative. Anywhere to the left of 0, my derivative will be positive. Anything to the right of 2, it'll be positive as well. Do you understand these positives are representing what the derivative is doing? The derivative is positive here. The derivative is negative. The derivative is positive. Here, the derivative is 0. Here, the derivative is 0. Makes sense? From now on, when I'm saying the derivative, I mean the slope of the tangent line. That's what I really mean, all right? So to say the derivative here is 0 means the slope of the tangent line here is 0. So let's begin to try and draw the derivative. And to draw it, what I'm going to do is I'm going to use use the things that are easy for me, that make, I guess, the most sense to start. And that is, I know that this right here, the derivative is 0 here, right? And 0 here. So if I go to draw this derivative, I should probably put, let me see what color I'm going to have here. At x equals 0, my derivative should be 0 here. And at x equals 2, my derivative should be 0 here as well. Okay, so this pink looking thing, that is my picture of the derivative. And I've given it, right now I have 2 points, right? Let's talk about what's happening. Let's start right here. I don't know why I want to start here, but let's talk about this. Think about those tangent lines. All these tangent lines here, they're all positive, right? But what's happening to them as you move to the right? What's happening to the steepness of those? What does it look like is happening? They're all positive, but what? Steeper,
Yeah.
steeper, 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 right? Which means bigger, bigger derivative. So when I draw my derivative to the right, it's got to go up and just keep going up like that. Now between 0 and 2, my derivative is always negative, right? But it starts, remember, it starts flat up here, and then it starts to slowly, gradually tilt over. It gets to like a steepest point right around here. It gets to a steepest point, and then it starts to gradually flatten back out again. Do y'all see that? It's like It's like a dipping down, then it gets to like a maximum dip, and then it starts to come back. So that means I start at 0 here. My derivative does, starts at 0, and then it comes down, gets to like a maximum negative somewhere around here, and then it starts to go back towards 0. And then on this side, I have, again, a tilting over. These are positive slopes, positive, but as I move to the left, these positive slopes get steeper, right? Which means my derivative must be big, getting bigger and positive. So my derivative must go like this out to the left. Let's take a poll, okay? Because like I said, this is like a yes, no. You either see it or you don't. So let's see how many of you understand what I'm doing here. Okay. Got a few that are a little confused still. We're gonna do another example. Hopefully after another example makes sense. 84% of you feel like you understand. Good. Okay, you ready to look at another one? Where is it? There it is. Okay. I am going to, am I going to work this one? I'm going to work this. I guess I'll work this one. Yeah. And I'll give you another one for you to work. All right. So for this one, notice, first of all, that like when Sophia did the first problem, right? You remember it was a line. And when it's a line, the derivative is always the same because it's a line, right? The slope of a line is constant. So this green is a line. So the derivative should always be the same over here, shouldn't it? It's whatever the slope of this line is. And then between these 2 points, we have, again, a straight line segment. So the derivative should always be the same here. And then here, this green is always going to be the same slope, but it'll be positive. So when we look at the left side, let me take this to a different, let me take this onto my other page so I can draw on it easier. Whoa. All right, so when I'm looking at this, if I want to, let's talk about what the derivative is doing over here. Well, like I said, it's always the same, right? Because it's a straight line. I'm not, yeah, it's a straight line. So I just need to figure out what the slope of this line is. Can y'all tell what it is? Can y'all tell if I just like pick 2 points and find the like rise over run of this?
1, 1.
1, 1, right? It's 1 that way and 1 this way. So the slope of that line is 1, which means the derivative should always be 1 over here, shouldn't it? So if I pick any x value over here, the derivative should always be 1, which means my derivative should look like this over here. Constant the whole time. Now, what happens at 0? This is the interesting point. Look at that top point. Because it's like like the tip of a triangle, it's hard to see what's going to happen here. You might think that the slope of the tangent line, you might be thinking, oh, the slope of the tangent line up there is 0. That might be what you're thinking, right? Because it would kind of balance on there. It's going to turn out to not be the case. All right. So for right now, I want you to ignore what's happening there. And let's talk about the red part. Okay. The red part. The red part should have a negative slope. And I think we can find the slope by doing the same thing, like picking a point, let's see here, and then down to here. Let's see, that goes what? Down 2, right? Down 2 into the right 1. So that should have a slope of -2, right? -2. Shoot, do I have enough room? Yeah. So doesn't that mean that on this blue region, that means between 0 and 2, my derivative should be -2. The derivative is always -2. So when I graph it, I go down here, -2 from here to here. That's what the derivative is. Let's not worry about what's happening at this bottom corner yet. And let's instead talk about what's happening on this last section, which is this green section here. The slope there, let's try and find the slope. Looks like, what, over 1 up 3? So it should have a slope of 3. So that means once I go past 2, my derivative should have a value of 3, which means it's up here. Questions? What's left for us to resolve is what's happening at these 2 points. And what we have here, and this is the first time we've seen this, is we have corners, okay? Sharp pointed corners. This is not like the previous example. The previous example, it was those edges, I don't have it. Those edges were rounded, right? They were kind of rounded peaks and valleys. Here we have corners. Anytime you have a corner, the derivative does not exist. You do not have a derivative there. So what that means is in my picture, I'm going to put an open circle right here and an open circle right here, and then an open circle right there and an open circle right here. The black graph is the derivative. F prime is the black graph. By the way, is the derivative a function? Is it a function? Look at it. Well, it passes the vertical line test, doesn't it? I mean, it does pass the vertical line test, right? So it is a function. It's a weird function. It's a step function. It like breaks and doesn't, but that is a function, okay? Because it passed the vertical line test. The name of this section, okay? Let me remind you what the name of this section is. The derivative as a function. We are trying to say, look, start with some function. Look at its derivative and realize that the derivative is a new function. All right. Start with the function. Derivative becomes a new function. They aren't the same functions, but they are related to one another, right? The derivative tells you all this information about the slope of the tangent line on the original function. Okay. Let's do another one. I'm going to let you try and draw the derivative of this one. Now, I need to say something before you try this. When we were doing this example, I was able to figure out the derivative precisely because these were straight lines and I could figure out the slope, right? On the example I did before this, when it was curvy, I couldn't find exact values of the derivative. I could just tell you it's positive, getting bigger, or negative, getting bigger. That's it, because there wasn't a precise way of calculating the slope. Here, we can see the slope easily because they're line segments. So what you're going to do with this one is try and draw me kind of a rough sketch of what the derivative of this would look like. All right, try it on your own. I'm going to redo the poll. Let me know when you're done. When you feel like you have a derivative drawn, let me know. And I'll break in once at least 60% of you are done. If you have a question, just ask right now. I'll stay on to hear you if you have a question. The instructions are to draw the derivative. I can give you all the hint that there is at least one point on this graph that you can tell me for sure the derivative has to be 0 there. The rest of it is just kind of you looking at it and analyzing it. We got almost half of you are done. Okay, that's almost everyone. All right, who wants to share kind of the general shape of what they got? I can call on Alec. Are you there, Alec?
Yeah.
Okay, so what did you get? Can you give me like 1 point for sure that you know is there?
I use my starting point as 0.
Okay, so you saw that at the bottom of this graph at 0, you know your derivative has to be 0 because there's a flat tangent line there, like that, right?
Correct.
So that means the derivative at 0 must be 0. So you have a point here for sure. Okay, and then what? What about
And
to the
then-
right? What about as you move to the right, what happens?
The slope is getting steeper, but it's positive.
It's positive. Okay, so your graph over the derivative should just go up over here, shouldn't it?
Mhm.
And then what about to the left?
It's getting negative.
Mhm. So it's going down like this.
Mhm.
So maybe something that looks like this.
Correct.
That seemed pretty close to what you have.
Mhm.
Everybody should have something close to like this. At 0, the slope is 0. To the right, the slope is positive, but it's getting bigger. So you can see it, as you move to the right, the black graph gets bigger. As you move to the left, these derivatives are negative, but as you move from right to left, these derivatives get steeper but negative, and so it should move down and to the left, or to the left and down. Now I have the computer, I can show you the computer do it. This is the actual like real derivative. This is what it looks like. It actually turns out to be a line. For a parabola, you're going to get a line, but we'll save that for another day. Okay, I have another one for you. We won't take as much time on this one, but I'll let you think about it for 1 minute. What would the derivative of this look like? Again, there is a point that you should be able to tell on this where the derivative is 0. Okay, that's about a minute. Devin, you there?
Yes, I'm here.
Okay, can you give me an idea of what you got?
Well, I know like 1 point for sure is going to be 0, 0, right?
Okay, 0, 0 definitely is there. Okay,
And then on both sides, it's going to be positive. So it's going to be going up on both left and the right.
like this.
Probably, yeah.
It almost looks like a parabola. Almost looks like a parabola. Because on the right side, if you go to any point on the graph on this right side, the slope of the tangent line is a positive, right? It's pitched up, then it starts to flatten out and become 0. And then on the other side, now you have still positive slopes, but they get steeper this way. So you're going to go to the right, positive numbers getting bigger, and to the left, positive numbers getting bigger. I really hope this is registering. Any questions? I have a question for you though. Let me ask you this. If I give you a line, like a flat horizontal line like this, the slope of that line is 0, right? And if I give you a line like this, you said that slope is positive. And if I give you a line that goes like that, you said that the slope here is negative, right? Well, what about a vertical line? What's the slope here?
Undefined.
Undefined. Undefined. Vertical lines have undefined slopes. Now, let me ask you this. What if I take a line that's vertical, but I tilt it just a little bit? So it's almost vertical, right? Just a little bit off from vertical. Would you all agree that this would be positive, right? Slope would be positive still, but huge. Huge, a huge number, yes? And if I tilt it the other way where it was slightly tilted like this, that slope would be negative, but it would be a huge negative number. Huge negative, yes? All right, you sure? All right, I'm going to make one up then. See if you can draw me the derivative of this. Here's the function. Here's f. The dotted line represents a horizontal asymptote. And then these both come in and kind of curve in and hit down here at the origin. Let me give you a minute or two on that one. This is a tricky one, but if you understand what's going on here, I think you can get this. I'll do the poll again. You can let me know if you think you have the derivative drawn. One thing that makes this one hard is that you don't have any points that you know for sure the derivative is 0. In fact, there's nowhere on this that the derivative is 0. My drawing kind of sucks, but let me kind of redo this over here. What I really want this to be doing is something like this. But I want that to come in very steep right there. I want the same thing over here. That's easier for me to draw. You ready to start talking about this? About half of you think that you have it, so we'll stop there. I'm going to show you, all right? I'm not going to call on anyone. The way I would do this is this. I would just go like pick a point, like maybe like right here. And I'd say, okay, here I know the slope of the tangent line is negative there, right? So I know I have to have a point down below the x-axis. And then if I move to the right, now I've still got negative, but now it's steeper, right? Which means I need to have a point further down. As I keep moving to the right, it gets steeper and steeper because it's trying to go into this point. So this is going to keep going down and down. And what I get is something that looks like this. And that is a vertical asymptote. Because remember I told you that where you have a corner like that, a point, you can't have a derivative exist. So there will be no derivative at 0. Now, on the other side of the function, I have a positive number here. So my derivative must be above the x-axis, so I'll just put it here. And then as I move a little bit to left, notice that these are still positive, but getting steeper and steeper, which means bigger and bigger positive numbers. And so what I get is something that looks like this, again, along that vertical asymptote. Let's stay on the right-hand side. As I move along here, what are these slopes doing? Right? They're all positive, but what are they starting to do?
What?
They're trying
Going
to
to
become,
0.
they're trying to become horizontal, right? They're trying to, but you're never going to get there because it's a horizontal asymptote. So you're still going closer and closer to it. There's still some pitch to the curve. The curve is still going up and up and up. So your derivative has to get closer and closer to 0 without actually getting there, which means it should look like this, and you should have a horizontal asymptote there. The same argument can be made on the other side. As you move to the left, these are negative slopes, and they're trying to flatten out, but they never actually truly flatten out. So they're negative, and they're getting closer and closer to 0. So negative and closer to 0 means the graph looks like this. Yes or no? Does that make sense or not? Does that picture of the red graph make sense as being the derivative of that other one?
I have
Okay,
a
good.
question.
Question? What?
Yes.
Yes.
So while I understand it, are you, okay, how do I phrase this? Why are the numbers on the derivative close to the zero? Why are they high positives? Up there, yeah.
Okay, yeah, okay, so think about, let's do this right here. This curve comes in here, right?
Is that
And it-
supposed to be steep?
It's supposed to be steep. It's supposed to be a steep coming in like this. Does that make sense?
Yes.
So as you start to kind of try and make that turn, you start to become these tangent lines. If you could zoom in, right? If you could zoom in, those tangent lines are starting to, you know, pitch over and start to become almost vertical, right? And we just said, right before this, we just said that if you have, you know, this case where you've got a little bit of a pitch to it, it's not quite vertical, then you're going to have a huge positive number, right? Huge positive number, which is why when I'm really close to zero, I'm really, really steep, almost vertical. And so I have a huge positive number coming out for the derivative.
Okay, that makes sense.
Okay. And the other side is the same thing, except negative because it's pitched the other way.
I just couldn't tell that that was that steep.
Yeah, my picture sucked.
No, I'm
It's-
sorry. I mean that I couldn't put that together.
Yeah, I should have exaggerated like this. I think that would have been better if I did that instead. Oh shit, now I just erased it. Okay. Okay. Yes, no, yeah, it's weird, right? So let me show you what the homework looks like. I really like the homework in this section. The first problem in the homework gives you a graph and asks you to estimate the value of the derivative at each point. So like, for example, if I wanted to, why aren't you drawing? If I wanted to estimate the derivative at -3, here's my y-axis, here's my x-axis. I go to -3, 1, 2, 3, there's -3. I go to this point and I think about drawing a tangent line here. And I try and estimate what the slope of that is. So for me, the way I drew it, it looks like maybe I go like down 1 over 1, 2, 3, 4, 5. So down 1 to the right 5, that's a -1/5 slope. That would be my estimate. And then you do that for different points on the graph. This question is, I would never ask you this on the test, but this is just again to get you to get the idea that when you're at different places, you should be able to tell, you know, if it's a positive or negative slope or zero, and then if it's a big or small number, right? The more steep it is, the bigger number it is. That's the first question, and I believe that's the second question. Same thing. Then the third question, I really like this question. They give you A, B, C, D. Okay, so they give you 4 graphs of 4 functions, and then they give you 4 graphs of 4 derivatives, and you're supposed to match which derivative goes with which graph. Okay. So, for example, on this one, remember we said with line segments, when you have a line segment, those have fixed slopes, right? So this should be like right here, we should have positive number, and it should always stay that same number, and then switch to a negative number and always be that negative number, and then back to a positive number. Well, that's this, right? It's positive, then switch to negative, then back up to positive. So this matches with this. And you do that for all of these. Make sense? Then these, they give you F and you go draw the derivative. So there's no matching here. This you have to do what I just asked you to do right now. Take that graph, go try and draw the derivative. So like for this one right here, there's the picture of what the derivative should look like. Okay. So that's the first part of the homework. I hope that all makes sense. What I want you to take away from this, again, is that now what we know is that if we start with the function f, the derivative is a new function. And if we have the picture of f, then we should be able to draw the picture of its derivative. Right? Okay. Back to the notes. So we want to kind of clear our minds a little bit now. All right. Clear our minds. We're done with the pictures now. And now we need to talk about some notation. So I don't know if I told you all this. Did I tell you all that there were two people who discovered calculus? Did I tell you all that in the beginning of class? No. So, you know, there was a point in time where calculus wasn't there, right? Humans had not come up with calculus. And there were two people that discovered calculus at exactly, well, about the same time in history. And they were completely independent. They didn't know each other existed. And they both came up with calculus. Isaac Newton was one, okay? So he's the father of calculus. And then the other one is Leibniz. The last name is Leibniz. I'll right here, it's Godfrey Leibniz, okay? One of the co-founders of calculus. And since these two men came up with this, they had their own notation. Like they were making this shit up, right? And so like when Newton was doing it, he was like, oh, I'll use this to represent the derivative. Okay, that's what he chose to use. Leibniz had the same concepts, but he used a different notation. He wrote dy over dx. And he said, you know, that was Leibniz's notation for the derivative. And so now that we have that, now that we know that there's different, you know, founders of calculus, we have different notations, and sometimes Newton's notation is easier to use and cleaner and makes things quick. Sometimes Leibniz notation is better. It just, you know, depends on what we're trying to do. So what we need to understand is that if you give me any function, y equals f of x, that all of these things mean the exact same thing. F prime of x means the derivative of that function. Y prime would mean the derivative of that function. Writing dy over dx means the derivative of that function. And all of these notations are exactly the same thing. The ones that we will use in this class are the first three. And you know what, this one also, okay? That one also. Those four is what we primarily use in this class. The other notations are more valuable when you get to Cal 3, because in Cal 3 you have more than just x and y. You have functions where you have more variables than just x. So you could have a function that has like 5 variables in it. And then you have to be real careful about keeping track of letters. And so the other notations, like this notation here, is really good because you can always change that x to a y or a z or l or m, and it'll make sense in Cal 3. I'm just trying to tell you that there's useful, all these notations are useful in different places and different classes, all right? It makes our life a little bit confusing though, because we have all these different notations. Okay, there has been historical evidence that Leibniz, there's a thought that Leibniz got a hold of Newton's work and that he perhaps plagiarized, and that Newton is really the only true founder of calculus. I've heard that recently. I don't know the merit of that, but people are kind of scratching their head looking at some of Leibniz stuff now going, huh, you know, he found that after this other thing by Newton was published. But okay, let's get out of that. This is not a math history class. Now I have to tell you a little bit more about Newton. So basically Newton went to school, right? And he absorbed all the math that was known at that point. Okay, so like imagine that you could go to college and you get to a point where you're like, oh, well, that's all we know. Like that's all the math we know. And they're like, yep, this is it. You know, and that's basically where he was. And so he went off kind of on his own, and he practically worked out of like a shed in his backyard. That would be what it would be like today. And in that little shed, he did the calculus, along with all his laws of motion and all that other stuff he did, right, in physics. Newton, of course, is one of the huge figures in science and humanity, right, like just in human history. But I've always thought that's pretty cool to be at a place in the timeline of the world where you can study something to the point that you get to a point that nobody's been there before. That's hard nowadays because, you know, humans have been thinking about things for a long time. So if you study math, it takes you a very, 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 very long time to get to a point where you're at a place where we're at the edge of the horizon. Does that make sense? Like, it takes a long time. That's why if you get a PhD in math, you have to study for many years before you even know what questions to even ask, what questions have not been answered. And it's like that for a lot of fields, you know? Okay, I'm going on a tangent. Derivative. All right, let's keep going. Differentiable functions. Okay, we need to define some things here. A function f is said to be differentiable at some point if the derivative exists. So we've been looking at functions and we've been saying, oh, look at the slope of the tangent line. Oh yeah, that's the derivative. Well, from now on, if the derivative exists, because remember the derivative is a limit. If the derivative exists, then we say that the function f is differentiable at that point. A function is said to be differentiable on an open interval if its derivative exists at every point in the interval. And most of the examples we've done today, our function was differentiable on intervals. So like if I go back to this example here, notice the derivative here. The derivative exists over here and the derivative exists over here, right? The derivative did not exist at 0. So you could say that the derivative existed from -infinity to 0 and from 0 to infinity, right? So out to the left of 0 and to the right of 0, you had a derivative. At 0, you didn't, right? That's what that definition is saying. Now, the next is a theorem that we're not going to prove, but it's a really kind of nice theorem. It says that if your function is differentiable at a point, okay, so if you have a slope of a tangent line, if you do, then I guarantee you it's continuous there, which means that you can draw it without picking up your pencil. I'll refer back to this later. Okay, that's just a theorem in the book. I want to make sure it's in my notes. The next topic is, when do functions fail to be differentiable? Some functions you can't take the derivative of. And there are three cases, that we will look at. A function will fail to be differentiable at a point A if there is a corner or cusp at A. I'll show you a picture in a second. If we have a jump at A, you can't be differentiable. And if you have a vertical tangent line, you can't be differentiable there. So let me show you the three examples. Look at this right here. I'm going to draw the derivative of this. Okay, so here comes the derivative. It's flat, right? Because the slope of tangent line there is always the same. And then when we get to that top point, look what happens to the derivative. Look at the green function. Boom, it jumps to the bottom, right? Anytime you have a corner or a cusp, you're going to have that break in the derivative. And that means the derivative doesn't exist here at 0. This is a corner. Does everyone see why that's a corner? You have a sharp corner? A cusp looks like this. That's a cusp. It's two curves coming together into a point. Okay, so at the corner, at that point on the cusp, you cannot have a derivative. The derivative does not exist there. It is not differentiable there. All right, the other one is where you have a jump. Okay, so anywhere you have a jump, you're going to have a problem with the derivative. And you can see it again here. If I come in from the left, I've got a positive derivative. And then where I have my jump, I have this changing of the derivative, and that's what causes it to not be differentiable. Only at that jump. And then the last place is if we have a vertical tangent line. I should have made these bigger, I'm sorry. So I want you to look at the derivative here. I'm going to draw it. The derivative is positive. It's getting steeper and steeper and steeper. So look at what the derivative is doing. It's taking off, right? And when you get to this point, it becomes vertical. And then you move over to the other side and you've got that same steepness. So do you see that the green function has a vertical asymptote? So you cannot have a derivative here in this case at 0, right? F prime of 0 does not exist. All right, the derivative at 0 doesn't exist. So corners and cusps, jumps, and vertical tangents. Anywhere you have a tangent line that becomes straight up, you're going to have a problem with the derivative. Back to notes. I'm going to skip this. That's just an interesting function, the Weierstrass function. So I'm not going to cover it. All right. Now, don't worry, the Weierstrass, it's not in your book either. So it's just something I throw in there and talk about if I have time. All right. So the next thing is I'm going to try and show this to you, see if this makes sense to you. Today, what we've learned is that if you start with a function f, we can do this thing called take the derivative of it, right? Find the derivative, and you get this new function f prime, right? So you start with the function. You do this operation called taking the derivative, right? And that actually requires that we do something. It requires that we do the limit as h goes to 0 of f of x plus h minus f of x all over h. We do this weird operation called differentiation. And when we do it, we get a new function, right? Which is called the derivative. Right? Start with a function, take the derivative, you get a new function called the derivative. Well, would y'all agree that this function here is just a function, right? Just start over. That's just a function, isn't it? So couldn't I do the derivative of that then? Like do that same thing again and then come up with a new function? Right? And then do it again because that's a new function. Just do it again. So I can keep on doing derivatives over and over and over. So we have this idea of what are called higher order derivatives. Now, right now, all we know is this, that if you start with the function, the derivative represents the slope of the tangent line, right? That's what it represents. If we do the derivative a second time, right now, we don't understand what that means. We will, but not yet. And if you do the derivative again, a third time, you have this third derivative, and like, what does that mean? Just, pause on that. We'll get to that. Right now, it's just to understand that we have these things called higher order derivatives. We know that this is the notation for the first derivative, right? You do an f with the little prime mark there. That means do the first derivative. Well, if we do f with 2 prime marks, that's the second derivative. That means you're going to take the derivative of the derivative. And if we do 3 prime marks, that means you're going to do the derivative of the derivative of the derivative. So the derivative 3 times. And you could keep doing this forever. And those prime marks become kind of stupid to keep doing primes, because what if you have the 8th derivative? You don't want to do 8 primes, right? So what we do instead is we write a number here in parentheses. It has to be in parentheses because look, if I write f with a 4 there like that, that means you're going to take the derivative 4 times. It's the 4th derivative. But if you write an f with a 4 here like that, that's an algebra notation. This means you take the f function and you raise it to the fourth power. Totally different operations, right? Those are totally different. So to distinguish between the two, we put a set of parentheses around the 4 to let you know we're talking about a derivative and not raising to a power. Fifth derivative, sixth derivative, and so on and so forth, all right? Now, that's Newton's notation. Leibniz, if you want to do higher order derivatives in Leibniz notation, here's what they look like. And I'm just going to grab one of these and show you what it is. So if I wanted to do the third derivative, I'd write d3y over dx3. And that means the third derivative. Notice that the 3's are offset here, right? Like the first 3 is after the d, but the second 3 is after the x. And the reason it's done that way is so that you, oh, oops, undo. How do I undo? Undo. The reason we do it that way is because if you accidentally write dy3 over dx3 like that, somebody might think you mean this, dy dx cubed. And that would mean the first derivative cubed. And that's not what we mean. We mean the derivative 3 times. All right. You look like you're having a great time. Let's do an example. I think it's time to actually do an example. Let f of x be equal to x squared plus 4x. I want us to find f triple prime of x. I want us to find the third derivative of this. All right. Here we go. All ready? I first have to find the first derivative, right? That's the first thing I have to do. So to find the first derivative, what I'm going to do is use the definition of the derivative, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. That is the new definition of the derivative. As we started class today, we replaced the a with x, right? And now let's figure out what this is. This is the limit h goes to 0. And Roberto, you there?
Yeah, I'm here.
Okay, so what, can you tell me what f of x plus h would be for us in this problem?
In this problem,
Yeah, in this
Okay.
particular problem, if I asked you to tell me algebraically, what is f of x plus h, what would you write down here for f of x plus h?
would just be f of x. I'm not sure entirely what you're asking.
I'm asking you to take x plus h and plug it into the f function for x.
Oh, okay, yes, okay, okay.
So
So,
what would that be?
would it just be x squared plus 4x plus h?
What you're doing, all you're doing is leaving that alone, just adding an h there. That's not what plugging x plus h would do. You have to replace that x and that x with x plus h,
Oh, yeah, okay, I remember now.
right?
Yeah,
So it should be what?
x plus h squared plus
Okay,
4x plus h.
and I need those in parentheses, right?
Yes.
Okay, everyone good with that? That's what f of x plus h looks like. And now we need to subtract from that. Let's subtract from that. That's this subtraction sign. F of x, right, everyone? So, David, you there?
Yes,
Okay, so what's f of x? I'm gonna put it right, this green piece. What's gonna go here?
x squared plus 4x.
Okay, x squared plus 4x. And is that good? Just leave it like that?
Yes, sir.
Yeah. You sure?
Yeah.
David, what about this minus sign?
Oh, you can translate it so it's going to be negative x squared plus minus 4x.
That's right. So that negative sign is going to have an impact. So if you're going to write that down, you have to put it in parentheses. That way you remember to put the minus through. That is a common mistake, is to forget to put the f of x in parentheses and then forget to distribute the negative through. Got it, David? Everyone?
Yes, sir.
Okay. All of this over h, right? Okay, we keep going. Limit h goes to 0. Now it's just a bunch of algebra. So I'm going to expand x plus h squared, which will be x squared plus 2xh plus h squared. I'm not showing that step, everyone. This expansion of x plus h squared is this. I'm not showing that. I'm assuming you know how to do that on the side, do FOIL, collect like terms. I'm also going to distribute the 4 through. So plus 4x plus 4h. And then I'm going to distribute the negative sign through David's part over here. Minus x squared minus 4x. The whole thing over h. So good? Questions? Good things happen. X squared, gone. 4x, gone. And everything that's left, y'all notice what everything that's left in the numerator has? What do they all have? What do all the terms in the numerator have in them?
H.
An h, which means I can factor an h out, right? I can factor an h out. If you did your homework, this probably looks somewhat familiar, except that we have x's instead of a's. And now I kill off the h's. At this point, I can let h go to 0, right? Go ahead and let h go to 0. So Chloe, what do I get if I let h go to 0 here?
You just get a 2x plus 4.
2x plus 4. Okay, good. There it is. Didn't we say that if we started with a function and took its derivative, you would get a new function? And isn't that just what happened? We started with x squared minus 4x, and we took the derivative and we got a new function, 2x plus 4. What's amazing about it is this. If I graph those two, right? If I graph x squared plus 4x, and now I graph 2x plus 4, do you all see that the blue line is the derivative of the red one? Go back and think about all these exercises we were doing. If I asked you to draw the derivative of the red one, right? What you would do is say, okay, well, I know down here, I know my slope of my tangent line is 0. So that means my derivative has to go through there. To the right, I get positive slope, so it should go up over here. And then to the left, these are all negative slopes, so it should go down over here. And in fact, that is exactly what that line is. There's its derivative. See that? That's the first derivative. I want the third derivative. So now what we're going to do is we're going to find the second derivative, we are going to take the limit as h goes to 0, but now we're working with this as our function. Do y'all understand that? We're going to be doing this one. So it's the same formula we had right here, this master formula for the derivative, but instead of using x squared plus 4x, we're going to use 2x plus h. And Enrique, you there? Aaron, you here? Or I'm sorry, Red. I don't see Red today. Shams, you there? Valerie.
Yes.
I'm striking out here, Valerie. Okay, so Valerie, using this formula right up here,
Mhm.
what would f of x plus h be for us if this is our new function?
It will be the 2 x plus
2.
h.
And then x plus h in parentheses, right?
Mhm.
And then
And 4 x
plus
H.
4. Okay, good. That takes care of the top left. And now minus what?
Minus the 2x plus 4.
Okay. And is that good or do I need something else here?
Parenthesis
Parenthesis, good, like that. And then all of this over
h.
h. And let's just see what happens algebraically. Limit h goes to 0. Okay, distribute the 2 through 2x plus 2h plus 4. Distribute the minus through minus 2x minus 4 all over h. And then again, we get good things to happen. 2x gone, 4's gone. And so now you have limit h goes to 0 of 2h over h, and the h's cancel, which just leaves you with 2. So let's go graph that. Y equals 2. And let me take the red one out of here. Right? We already knew that if we started with the original function f, that when we took its derivative, we got that function, right? And now forget the red one. Let's just act like that's a new function and let's talk about its derivative. Well, it's a line, right? So whatever the slope of that line is what the derivative should be. And we said the slope of that line was 2. Can anyone guess what the derivative of that's going to be?
0.
Should be 0, right? It should be. Let's see. Let's do the work. So now we have this new function, right? This new function. And I'm going to now find f triple prime of x, which should be the limit as h goes to 0. And then we have to use that formula, right? Up here, we have to use this formula. We have to plug x plus h in and then subtract what we get when we plug x in, right? Plug in x plus h, plug in x. But the function is a constant function, isn't it? So what happens when you plug x plus h into it? It's just 2, right? And x plus h has no impact on it. So that's just 2 minus, now plug x into it. Well, again, there's no x in this function, so it's 2 again. And then over h. And that's just limit h goes to 0 of 0 over h. Now look, this is a subtle thing here. The numerator is the number 0. This is 0. I'm not saying it's approaching 0. I'm saying it is 0, right? 2 minus 2 is 0. And so I just don't want you to think that right now we have 0 over 0 and this is bad. We have the exact number 0 on top, which means that the denominator doesn't matter. If the numerator is 0, not approaching 0, if it is 0, then the answer to this will be 0. And of course, that's what we said we thought it would be, right? Okay. It's 2:30. Let's see where we are in the notes here. Yeah. Last topic. This is one application of this concept, all right? This is one application. This note says that if you start with some function, s equals f of t. All right, so we're using s, and then some function, we're using t as a variable. T is like the x has been for us, but we're using t because it's going to represent time. So it says, let's say you have a function that gives you the linear displacement or position of an object at points in time. Right, so you have some function that tells you exactly where something is at every point in time. Then the derivative of that function, the first derivative, will give you the instantaneous velocity of the function. Okay, so start with the position function. The first derivative will give you the velocity function. And then if you do the derivative again, you will get the acceleration function. So you start with position, first derivative gives you velocity, second derivative gives you acceleration. In a physics class, this comes up. You'll start with, they'll tell you, oh, a spring is attached, a weight is attached to a spring and it's oscillating. And they say, here's the position function. And then they ask you something about the velocity. And you're like, what? How the hell am I supposed to get velocity from position? By taking the derivative. You have to take derivative of the function, and then you can talk about its velocity. So let me see. I think I can probably do an example here. So let's do this one. I wonder if you've seen this before. S of t equals negative 16t squared. You know what? Hold on. Let's just do that. Let's just say that this is our position function. All right, I'm giving you that that's position. Let's say it's given in feet. So the position in feet, and then let me just tell you that time here is given in seconds. Then if we take the derivative of this, whatever that is going to be the velocity. And that the units of this would be in feet per second. And if we do the second derivative, then this is going to give us the acceleration function. And that will be given to us in feet per second per second. I'm not going to have time to do this problem, but you can imagine what you would have to do here, right? I think maybe you would take the limit as h goes to 0 of s of t plus h minus s of t all over h. So it's basically that same generic formula for the derivative. Right, this is our generic formula. But instead of having f as being the name of the function, it's s. And instead of using the variable x, we're using t. And so you're just going to play the same game. You start off by plugging t plus h in here, and then plugging t into here and subtracting and dividing by h, and things will cancel, and you should get a first derivative. And then you take derivative of that, do it again, and then you get your second derivative. You're just going to have to practice on this. How are y'all feeling? How does today feel? Huh? All right, let's do this. I'm going to go back to our calendar, okay? The homework for 2.2, I looked at it earlier. Do everything except 13. That's a lot of problems. The first, all the way up through 11 is where you're, drawing pictures and matching the stuff I showed you before. Once you get to 19, it's 19 through 27. Those are very important problems, because all of those you're asked to find the derivative. So all of those are limit problems, right? Where you're applying the formula from the beginning of class. F prime of x equals limit h goes 0, f of x plus h minus f of x all over h. And then you're doing all the algebra to get it to work out. And at the end, you get a new function. And then 33 through 36 is asking you to look at a function and tell me where it's not differentiable. So you're looking for corners, cusps, jumps, and vertical tangents. And you're just trying to say, oh yeah, right here you won't have a derivative there, you won't have a derivative here. So those are important problems, but 19 through 27, those problems right there, those are the big ones for this section. Questions? All right, so what we do next class, okay, after you suffer through 19 through 27 and realize that taking derivatives, like finding derivatives with the limit sucks, after you realize that, like all the algebra in there, next class we'll say, you know what, like I told you this already, we'll put the formula away, we'll get rid of the limit, and we'll get all these nice little shortcuts. So you're going to be like, yes. Now I know you want to leave, but I just realized I still have 3 minutes. I'm going to show you something. No questions? We'll need this for next class. All right, let me see what I can do here. I want to talk about what are called binomial expansions. So just follow me here. If I tell you take x plus h and raise it to the 0 power, what do you get? Anything to the 0 should give you 1. Thank you, Chloe. Okay, what if I tell you take x plus h and raise it to the 1st power? You will get just x plus h, right? Okay, I'm going to write it like this, x plus h. You'll see why I'm doing this in a moment. Now I'd like you to take x plus h and I'd like for you to square it. So that means you have to FOIL it out, right? Now I'm not going to show the work, but we've done this a few times. And I hope that you agree with me that it would come out to be this, x squared plus 2xh plus h squared. Right? I think we've seen it enough in our lives that maybe we would agree with that. Now, if I do x plus h to the 3rd power, I can multiply that out also, and it would take me a little bit of time. Here's what you would get. X cubed plus 3x squared h plus 3xh squared plus h cubed. If you believe me, that's what it would become. Now, if you do x plus h to the 4th power, that's x plus h times x plus h times x plus h times x plus h. Here's what it becomes. X to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. All right, so this should be like, oh shit, you know, like what's going on here, right? Am I that good? Do y'all think I'm that good? Do you think I know how to do? I'm just doing this all in my head. I'm not that good. Okay, look. So how about this? X plus h to the 5th is going to be x to the 5th plus 5x to the 4th h plus 10x cubed h squared plus 10x squared h, hold on, h cubed plus 5x h to the 4th plus h to the 5th. Now, I don't have these memorized. I don't know, you know, what these are. I'm not doing them in my head. There's a pattern here. Okay, there's a pattern. Has anyone ever seen this before? Maybe some of you. Okay, so let's take a look right now. I want you to focus right now just on the coefficients. If you have to go, you can go. We're almost done here. Just the numbers in front of all these letters. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. You see those? I'm going to just write those numbers without all the variables. It was 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Can anybody tell me what the next row is going to be?
1, 6, 12. That'd be
Not
12.
12, not 12,
14.
not 14.
20.
No. There is a 20. The 20 is here. But there's a number in front of it.
15.
15. Good. How about the number after 20?
It's another 15.
Another 15. After 15? After 15?
6 and
After
then
6?
1.
1. Okay, so this is the pattern. To get the next number, it's always the 2 above it added together. And you always have 1s on the ends. All right, so like if you start off from the very beginning, you have a 1 and then 1, 1. That's the way it starts. And then you go, oh, these two give you 1 and 1 give you 2. And then you always put 1s on the ends. So then the 1 and 2 give you 3, the 2 and 1 give you 3. And then the 1 and 3 give you 4, 3 and 3, 6. Got it? This is called Pascal's triangle. Right, triangle. All right. Now, that's what's happening with the numbers. In terms of the letters, the variables, it's a simple pattern. Look at the X's. Just the X's. Tell me what's happening as I move from left to right.
They're decreasing in number.
Decreasing power. And they always start with the power we have here, right? 5th power, X to the 5th, X to the 4th, cubed, squared, X, gone. What about the H's?
They're increasing in power.
It's the opposite, right? No H, H squared, H cubed, H to the 4th, H to the 5th. So my next line, okay, my next line would be X plus H to the 6th would be, well, there's a 1, and then X to the 6th. Plus, now the next number is the 1 and the 5 added together, that's 6. Now my power on X comes down, X to the 5th, power on H comes up. Plus, now I take the 5 and the 10 added together, get the 15. Now my X power comes down, H power goes up. I've done 5 and 10, now I do 10 and 10, that's 20. The X power comes down, X cubed, H power comes up, H cubed. Plus I've done 10 and 10, now I do 5 and 10. So 15, and now X power goes down, H power comes up. Now I need 5 and 1, that's 6. So 6, X is going to go down to X squared is going to go down to X, H to the 4th goes H to the 5th. And then the very last one plus 1 H to the 6th. These are called the binomial expansions. Believe it or not, I'm going to need this to prove to you one of the formulas that we're going to use. All right. So this is not for nothing. This saved me some time. I don't have to use it at the end of, or at the beginning of class next time. I'll refer back to this when we start next class. Okay, everyone. Thank you for hanging out. Have a great weekend. If there are any questions, I'll hang out for a minute.
Thank you.
Thank you, Professor.